All right, so we're doing 11.7 today. How can we compare distributions? And we're going to leave it at that. And we're going to jump right into the first question here and start comparing distributions using our z-scores. So example 1, international swimming. The mean time for the men's 100-meter freestyle is 50.46, the standard deviation of 0.6 a second. For the 200-meter freestyle, the mean time is 110, with a standard deviation of 1.4 seconds. Keywords here. Assume the international swim times are normally distributed. That means they follow that lovely curve that you've seen so much that you just enjoy. Makes you feel all warm and fuzzy inside, right? Anyways, if an athlete's best time for the 100-meter is 48.76 seconds, and for the 200-meter is 100.43 seconds, and he can only enter one event, right? Maybe, I don't know, to be fair, or just because his coach won't let him, whatever the case. All right. Which one should he enter? And you're going to use statistical analysis to support your answer. So the idea here is find yourself a z-score. What's kind of nice about z-scores is that you can compare things that people wouldn't normally compare. So for example, let's say you have two farmers, and one's an apple farmer and one's an orange farmer, and you know the means of them. Well, if they're normally distributed, the weight of these apples and oranges, you can actually figure out which farmer has better or grows larger apples compared to the mean versus oranges compared to the mean. And you can actually compare apples to oranges, and I'll explain a little more after we get through this question. But you know that saying, you can't compare apples to oranges? Well, in statistics, you actually can. Maybe not so much taste, but the size and the weight of it, you totally can. I think that's kind of cool. So, all right, let's draw our two normal curves. Get a nice picture because, you know, those are worth thousands of words, they say. All right, so we have the 100-meter. Come on, get going. It's tough to draw when the line is lagging behind you. Anyways, so we have the mean of the 100-meter was 50.46 with a standard deviation of 0.6. And then we had the other one, which was a much nicer curve, the 200, and the mean was 110.4. 110.4 with a standard deviation of 1.4. All right, so what are the times that we have? So for the 100-meter, the time is 48.76. Not a bad time. And for the 200-meter, the time is 108.43. Now, anyone can look at this, you know, and say, hey, look at this, they're both less. They're both less, right? And the distance here is definitely more, and the distance here isn't quite as much, right? But they're both pretty close to being about 2 seconds less. But which one is the guy more likely to win? Well, just because it's farther away doesn't necessarily mean he's more likely to win this event because there's more time in between here. What really matters is the standard deviation. So what we need to find is the z-score. Again, on both of these, we already know what the z-score is for the mean. So this is, again, z equals 0. This is our z equals 0. What we care about is what is this z-score? And what is this z-score? How far off to the side are we? So, again, z-scores are pretty easy. Some number minus the mean all over the standard deviation. Be careful because the standard deviation is different for each one. This one is over 0.6. When you type it in your calculator and you hit enter, you get 2.83. That's supposed to be an 8. It's just an ugly 8. All right, for the other one, we have z equals, again, the sum number this time is 108.43 minus the mean, 110.4, all over, what was it, 1.4 here. Go to your calculator, type it on in, and you get negative 1.407. What you should notice is that both of these are negative. Why are they negative? Well, the number was to the left-hand side. You should expect that. A number over here should be a negative z-score. A number over here or over here should be a positive z-score. If that's not happening, it means you did something wrong and you should look at your numbers. Oftentimes I see people confuse these two. They switch the order here and then they get wrong answers. So which event, all right, should he enter? Well, which event is he farther from the mean is the question. All right, so in the 100-meter, he is 2.83 standard deviations below the mean. But in the 200 meter, he is only 1.4 standard deviations below the mean. So which one is he better at? Well, obviously that's going to be the 100 meter because he is 2.83 standard deviations better than the average person. Okay? If you were to figure out the percentages, there would be a far smaller percent here than there would be here. And those are the percent of people that are better than him. So if we figured this percent out, it would tell us blank percent are better than him. There's going to be a lot more here, higher percentage, because that z-score isn't as far from the mean. So to answer the question, he should enter the 100 meter event because he is 2.83 standard deviations lower than the mean, as opposed to the 200 where he is 1.4 standard deviations below the mean. All right, so I took the time to write it down so you wouldn't have to see me erase a million times. That took me a bit to get it to write that nice. So here we go. I'll read it off to you. He should enter the 100 meter event. He is 2.8 standard deviations below the mean compared to the 200 meter event where he is only 1.4 standard deviations below the mean. Now I abbreviated standard deviation with SD. That's fine to do. You'll be okay with that. So while you're copying that, because I'm sure it'll take a little bit, I'm going to talk about that apples and oranges problem. So when you have those two farmers and they're trying to figure out who grows the bigger, heavier, we'll go with heavier, I guess, heavier fruit compared to the average, these people, right, want to be, the farmers want to be farther, more standard deviations above the mean, as opposed to, who is it, this athlete that's swimming, I don't think there was a name, but anyways, because a swimmer wants the faster time, so you want to be farther below the mean. But when we're talking about those farmers and we're comparing an apple farmer to an orange farmer, you want the weight to be heavier, so you want to be more standard deviations above the mean. So you do need to think about your question. Sometimes it's you want to be farther below, sometimes farther above. But that's the idea. So in this case, he should enter the 100 meter because he is 2.8 standard deviations below the mean compared to the 200 meter where he's only 1.4 below the mean. All right, let's move on. So example 2. Speeds of vehicles along a stretch of highway are normally distributed with a mean of 56 miles per hour and standard deviation of 4. If one vehicle was determined to have a z-score of positive 1.96, determine the speed of this vehicle. All right. And then another one was negative 1.38, determine the speed of that vehicle. So here we go. So we're going to draw our curve, come up with what it looks like. It says the mean of 56, so that goes right in the middle. It's not telling us the sum number. That's the interesting part. But it did tell us what the z-score was, and that's why I keep writing the z-score above or below the sum number each time after we find it. So you make that connection. The 56 is really just a z-score of 0, and we want to find that sum number. So in this case, we're going to have to work backwards. We know that z is equal to sum number minus the mean over the standard deviation, and we actually have everything we need. We have the z-score. The sum number we don't know, but we do have the mean. All over the standard deviation, we're told, is 4. This is just a basic cross-multiply algebraic problem. So we multiply 4 times the 1.96, or put this over 1 if you need to see it like that first. There's nothing wrong with that. So 4 multiplied by the 1.96 is going to give us 7.84. That equals x minus the 56 because, well, anything times 1 is itself. So we cross-multiplied. Add over 56, and life is good. You get x equals, come on, right, 63.84. So it didn't tell us what around. Should have probably, but that's going to be the answer, 63.84. And we're good to go. If another vehicle was determined to have a z-score of negative 1.38, so why don't you try this one on your own based off of the previous problem. I'm going to pause it, and then I'll show you the answer. All right, so here we have it. Sum number, or value minus the mean, over the standard deviation equals z. Negative 1.38 is that z-score. They told us that. Cross multiply gives us negative 5.52. Add over 56, and you get x equals 50.48. So that's the speed that the vehicle was traveling if the z-score was negative 1.38. So again, that sucker was right there. That's that answer. All right, let's move on to the last question. All right, so example 3, 2 versions of a standardized test are given, an April and a May version. A little typo for the April version, a mean score of 480 and the standard deviation 24. the statistics for that's the word that's missing in the first part, for the May version show us a mean score of 510 and a standard deviation of 20. Again, key word here, most important part, normally distributed. Joanne took the April version and scored in the interval 510 to 540. What is the probability to the nearest 10 thousandths that a test paper selected at random from the April version scored in the same interval? So she scored between 510 and 540, and that's what they really want us to find. So it's kind of a weird question. It's going back to what we did last class, finding the percent in between an interval. So that's what we're going to do first. So what is the percent of scores between 510 and 540? Now it said the mean for the April version was 480. The mean always goes in the middle. We care about 510 up to, what was it, 540? So this is the area that we would like to find. We need to find those z-scores. So z equals and z equals. So again, same thing that we've been doing over and over again. I'm sure you're sick of it. It's some number, the value minus the mean. So 510 minus the 480 all over the standard deviation, which it says for the April version is 24. That's going to give us a z-score of 1.25. Do the next one. We have 540, I apologize, is the sum number, minus the mean, which is still 480, all over the 24. That gives us a z-score of 2.5. So we have our 1.25 here, and our 2.5 here. So we are finding the probability that z is in between those values. This was the easier version of the question from last class. We have our upper bound, 1.25, our lower bound, which is 1.25, and our upper bound, which is 2.5. Hit enter at the calculator, and you should find out that your answer is 0.0994. So nearest 10,000 should go 4 places. Yep, that's not going to work. 0.0994. All right, here's where the question gets tricky. Maria took the May version. In what interval must Maria score to claim she scored as well as Joan? So she can't just say, hey, she scored, in the interval 510 to 540, because that would not be the same. All right, we have to be in the same z-score. So we have to figure out what those z-scores were, which we already did, and then we have to use those same z-scores for the May version. So let's draw the May version. Oh, it's okay if you're not quite getting it just yet. I'll explain it again. So the May version was different. We had a mean of 510, and we want to be in the same interval. We want to have the exact same area. So what I want to know is, what is this score here? That's supposed to be a question mark. And what is this score here that would give me this exact same area, which happens to be 0.0994, which is what this guy right here represented, 0.0994. To do that, to get that exact same area, I have to have the exact same z values, z-scores, that Joanne had on the April version. So I already know what my z-scores are. So z equals 1.25 and z equals 2.5. So this is just a work backwards question twice, but it is definitely a confusing question. So let's plug in. We have our value minus mean, z equals that. So 1.25 equals the value, which we don't know, that's x, minus the mean, 510, over the standard deviation for the May version, which was different, it's 20. Got to be careful. I hope you can't hear all the walkie-talkies in the background, but I'm sorry if you can. They are doing a lot of talking. Cross multiply and solve. So 20 times 1.25 is 25, equals x minus the 510. Add 510 over, and you get x equals 535. So that is going to be the low value. To find the upper bound, again, we'll use the same formula, z equals, so it's 2.5, equals some number, the other x value that we have, minus the mean, still 510, all over 20, standard deviation. That's horrible. Cross multiply. you end up with 50 equals x minus 510. You add over 510 and you get the other x value is 560. So the interval from 535 to 560 on the May version, because it had a different mean and standard deviation. Looks like it was a little bit easier in May. Students did a little bit better, or the April version was harder. Either way you want to look at it. All right, don't forget to do your summary and your practice problems. Thank you.